Welcome. Welcome to Presto. You got it. Where we use insight for comments and analysis to make your learning easy, interesting, and fun. In addition, on academyforadvancedstudy.com, at very affordable price, we offer many tutoring programs to help you. We cover SAT, ACT, AP, all the college prep materials. Of course, we cover many K-12 subjects. We even cover college-level materials. Again, at very affordable price, we offer tutoring programs for advanced topics in statistics, computer science, data science. We also cover programming and engineering, Python, Java, JavaScript, HTML, CSS, everything you need in the age of AI. If you want to go to medical school, we can help you too. Again, at a very affordable price, we offer tutoring programs to help you with your MCAT. Now, let's go back to our talk today. What we're going to do today is to continue our conversation about regression evaluation matrix. So far we have talked about mean absolute error, MAE, mean squared error, MSE, and the root mean squared error, RMSE. All of these, they are used to guide the algorithm to minimize the error, and so we can produce the best or optimal model. What we're going to talk today is coefficient of determination. This is a little bit tricky. Usually people, when people talking about this, they do not think this as a regression evaluation matrix. When people talk about this, it's about how much variance in the data can be accounted for by the model. But actually it's quite related, but not exactly the same aspect as the other three we have talked about so far, the mean absolute error and mean squared error. But it's actually quite important. It offers something on top of what we have talked so far. So let's start our conversation today. All of the matrix so far compare the discrepancy between the predicted and the actual values in order to evaluate the model, in the sense to determine the best or optimal model. However, in reality, there is some natural random variance in the daily sales of ice cream that the model takes into account. We will come back to this in a moment. In the linear regression model, the training algorithm fits a straight line that minimizes the mean variance between the function and the known label values. So that's essentially what the model is. It tries to minimize the discrepancy. The coefficient of determination, more commonly referred to as R squared, is a matrix that measures the proportion of variance in the validation results that can be explained by the model, as opposed to some anomalous aspect of the validation data. For example, a day with a highly unusual number of ice cream sales because of a local festival. This is a long sentence, and it's not very clear what they are trying to say here, actually. But to make a very intuitive comprehension of what's going on here is that this is something quite different, the R squared coefficient of determination. The way to appreciate this is that the natural phenomena usually it's quite complex, and so in terms of ice cream sales, you may have a very good day if one family comes to town to have a family reunion. Suddenly you have thousands or even hundreds of people coming, and they are enjoying the summer, enjoying the ice cream. So you're going to have a good day, or you have a good day because a group of students come to visit a museum in town. So they take a break, they buy a lot of ice cream from you, and you're going to have a good day. And but on the other hand, if suppose all the people, everybody, or most people, want to see a football game, then you are not going to sell a lot of ice creams. So all of this can happen, and all of this can affect your ice cream sales. The point here is that the natural phenomenon, the real life scenario, it's quite complex, usually much complex than what our model can predict, and we have to recognize that. And this is very important because even when we are doing our best, minimize all the error. So the key thing here is that we minimize the error. But is that good enough? Right? We did the best we can. We use the perfect matrix, for example, mean squared error. But yeah, that's optimal result based on that perspective. But if the nature of phenomena is such that it's much more complex than our model can ever be possibly explained, then perhaps we need to be careful when we want to use our model to predict something, to guide our sales, to guide our decision making. So that's a key thing here. This is actually quite important to appreciate. So this is the main point of a coefficient determination. Another way to appreciate this is that to explain a complex scenario, we probably need a richer model. So, for example, if our model right now all we have is one feature, that is a temperature. But if we have second parameter, second feature, for example, the calendar date, and suppose the town will have that festival like the beginning of summer. Suppose it's first Sunday of summer, then in that case we can tell with a little bit of variance that if we use a calendar date, or even if we use a value to specify if it's first Sunday of the summer, then we can have a model that takes into two features into account: the temperature and the calendar date, or if that date is the first Sunday of the summer. With that richer model, we will be able to predict the ice cream sales much better, because we have some factor to account for if the town is having that festival on that day. So what it means is that if we have a richer model, we will be able to account for more variance. We can account for more complexity in the natural phenomenon we are working with. So that's a key thing here. Now let's take a look at what mathematically this R is, or this R squared is actually. The calculation for R squared is more complex than for the previous matrix. It's quite interesting. It's actually it's complex, but it's quite interesting. it compares the sum squared difference between predicted and actual labels with the sum of squared differences between the actual label values and the mean of actual label values, like this. Well, yes, we do need this break like this. We do need the break from this very long sentence so we can make sense what's going on here. But it's actually not very good, this formula here. We need better presentation. Luckily, we do have such a much better presentation. Yeah. So actually here we have some material to cover the correlation coefficient and the coefficient of determination. Hopefully one day we can produce a talk to help you appreciate the relationship and the difference between these two. And to give you a break, I will give you quite a few formula for you to accompany your dinner. And actually, what we're looking for here is this one, r squared. So this is much better presentation than what we had from Mr. Microsoft. So here, what we have is two terms on the right hand side. The first term is very simple, just 1. The second term is a fraction. One thing to notice is that that fraction value must be positive. Why? Because both the numerator and the denominator, they are sum of squared. So anything squared is always positive. And when you have a sum, it will probably positive, and at most it's going to be 0, but very unlikely. So most likely both numbers, numerator and the denominator, they are going to be positive numbers. So and also we can show that that number is always smaller than 1. With that, we can examine at a higher level first. So when 1 minus a number, if the second number here is large, then the difference is going to be very close to 0. A number for r squared close to 0 means that our model is not doing a great job to explain the natural complexity or natural variance in the natural phenomena we're working with. Sometimes it's just the nature of the phenomenon. Sometimes it shows our model is not rich enough. So but if the second term, the number is quite small, then the difference between that and 1 is going to be quite close to 1. In that case, we can say, well, our model can explain a lot of variance or complexity. So it's very important for us to recognize variance measures complexity. That complexity is a concept very closer to our daily experience. So not something very abstract. Variance. What does that mean? So with that established, let's focus on the second term. Second term, we have one thing to remember, or actually to enjoy. Actually, that's probably a better term. One thing to enjoy is that the second term is the relative performance of our model. So we'll come back to this concept in a moment. But the key word here is it's a performance, but it's a relative performance. Relative to what? Relative to the denominator, relative to the inherent complexity of the phenomenon. So now let's talk about the denominator of the second term of this fraction here. The denominator, let's forget about the sum, let's forget about square. let's just focus on what's inside that pair of parentheses. We have yi minus y bar. Y bar is the average of the label values, and yi is the label value for each entry, for each data point. So we can use a few examples here to explain what this means. So suppose what we are measuring is a person's height over age 18. So usually it's going to be quite stable. So that number, it may vary a little bit between, say, from morning to afternoon, between like the spring and the winter. I don't know about that. And then, but no matter what, it's not going to vary too much. So it's quite stable. It's not, in other words, it's not very complex. You're not going to suddenly gain a few inches in a few hours. So it's not going to be very complex, not going to vary a lot. But in that kind of situation, the yi minus y bar, the number is not going to be very big, and either it be a positive or negative number. The absolute value is not going to be very big. And when you sum all these small numbers together, that sum of squared is not going to be very big either. So what it shows is that in this case, the complexity of the natural phenomena we're working with here is not very big. So in that case, our model better to perform quite well, relatively speaking. If our model produces a numerator that is big compared to the denominator, then it shows our model is not doing a very good job. Let's examine a different scenario. Suppose the numerator, the nature of a phenomenon we are studying, is the temperature of a day. So for a year, then the temperature can vary quite a bit from spring to summer to fall to the winter. So it's quite complex. The y bar, yeah, we're going to have a y bar, but the yi minus y bar is going to be it's going to vary quite a bit. In that case, the phenomena is much more complex than the first phenomenon we're studying, a person's height after age 18. In that case, the denominator is not going to be very small because the y bar may be somewhere in the middle, right? But summer and the winter, the difference is going to be big. And when you square that number, it may become bigger. So in this case, the phenomenon is more complex. Then now we are ready to talk about the numerator. Numerator is the measure of the absolute performance of our model. So absolute in the sense that we do not take into account the natural complexity of the natural phenomena we're working with. So the absolute performance is yi minus yi hat. This is what we have been working with for a little while now. So y hat is the predicted value, yi is the label value, actual label value for that ith entry. So if our model is performing really well, these two numbers, they are going to be very close. The number, the value before square is not going to be very big, and after square is not going to be very big either. And when we sum, it's not going to be very big. So in that case, the number, relatively speaking, we will examine the influence of the denominator in a little bit. then it's not going to be very big. So when it is subtracted from 1 from the first term, the value is going to be close to 1, which means our model is performing quite well in the sense that it accounts for a large or majority of the variance or complexity in the natural phenomenon. So that's the absolute performance of our model. That's top. That's the numerator here. But what matters is the relative performance. So if our model produces a numerator that is small, but compared to the complexity of phenomena here, suppose it's about the first scenario, a person's height. If this comparison is not very favorable, meaning our numerator is small but not that small compared to the denominator, then the fraction, the division here, what it will produce is a number very closer to 1. Once we subtract the number from the first term 1, we're going to have a number very close to 0, which means our model is not explaining a lot of variance or complexity in the phenomenon that we are working with. So this is what the relative performance means. But on the other hand, if suppose we are working with predicting temperature of a day, then we may have a large number for the numerator, but if the denominator, the bottom, is also quite a big number, then perhaps the division, the fraction, will give us a number quite small. And if we subtract that small number from first term 1, then the difference will still be quite close to 1. In that case, even it is a case that our numerator, the absolute performance of our model is big, but the relative performance of our model is still actually quite good. So the number for R squared is going to be a number that very close to 1. So that's what we meant, that the second term measures the relative performance of our model. So that's a very intuitive explanation of R squared, or coefficient of determination. Hopefully you enjoy that. Yeah, life is actually not that bad when you can study a math formula during your break. So now we are ready to skip this very nice formula here, and they recognize that don't worry too much if that looks complicated. Most machine learning tools can calculate the matrix for you. They better do that. The important point is that the result is a value between 0 and 1 that describes the proportion of variance explained by the model. The better way to explain this is to the complexity. So variance equals complexity. In simple terms, actually they are talking about simple terms. That's some progress. The closer to 1 this value is, the better the model is fitting the validation data. In the case of the ice cream regression model, the R squared calculated from the validation data is 0.95. It's actually quite good. 0.95 is a very good number for R squared. So we're going to have a talk to help you evaluate what number or what value of R squared is good and what value is not so good. Oh, okay, we finally finished our section about coefficient of determination, or R squared. I hope you enjoy that. I do. I have to. Now we are ready to talk about iterative training. This is actually very important because life is tough, and you have to sometimes the same thing over and over again, hope to have a different outcome. The matrix described above are commonly used to evaluate a regression model. In most real-world scenarios, a data scientist will use an iterative process to repeatedly train and evaluate a model. And varying, okay, this is what she will do. Number one, feature selection and preparation, choosing which features to include in the model, and calculations applied to them to help ensure better fit. So what it means that, for example, in our ice cream sales situation, if we only have temperature, we may not be able to account for the sudden jump of sales on that festival. But if we have two features, the temperature and the if that day is day of the festival, then we can explain quite a bit of how many ice creams we're going to sell that day. So that's a feature selection and also calculation applied to them. What it means is sometimes we have to do some transformation. The nature of the data may not give us a very good, simple linear regression model. So in that kind of situation, we need to do some transformation, or in other words, some calculation to make our analysis or model building or training much easier. So that's the first thing that data science needs to try. Number two, algorithm selection. We explored the linear regression in the previous example, but there are many other regression algorithms. Yeah, life is good. You can have other algorithms, actually much more complex than simple linear regression. Number three, what we meant for the second point is that you may need to try different algorithms to see which one perform better. Number three, algorithm parameters, numeric settings to control algorithm behavior, more accurately called hyperparameters, to differentiate them from the x and y parameters. That's a long sentence. What it means that there are parameters, there are hyperparameters. Hyperparameters is not what is built or trained based on the data. They are set by the data scientist based on all kinds of considerations. So the key thing here is that you do not set those hyperparameters based on the data. That's based on your consideration, your insights, your investigation. Or more precisely, it's those hyperparameters cannot be determined by the training session. So after multiple iterations, the model that results in the best evaluation metric that's acceptable for the specific scenario is selected. Yeah. So hopefully that's the outcome. If the outcome is that none of this will meet your needs, then you better find another way to do that. So the key thing here is that it's not just the best model. It also have to be the model that meets your needs. Both conditions have to be satisfied. All right, so that's all we have for you today. Remember, on academyforadvancedstudy.com and academyforadvancedstudy@gmail.com, at very affordable price, we offer many tutoring programs to help you. That's all we have for you today. Thank you. Have a great day.